And okay. And excuse me for the sound effects around because I'm broadcasting from my virtual bureau, so it is out of my control. The virtual floor is yours, Ola. Please go ahead.
All right, thank you, Jakub. Yeah, so I'm Ola Rønning. I'm a PhD student at Copenhagen University in Thomas Hamelryck's group, and Christoph Lai, who's also here, is my co-supervisor. So, and we'll be talking about an inference algorithm called ELBO-within-Stein today. In particular, we're going to be taking the view of machine learning statistics as sort of trying to match a finite set of data, potentially a stream, to a hypothesis, which is going to take the form of some probabilistic model of probability distribution. Now, to sort of do something with this, we're going to be working with divergences. So we're going to be working with the sort of distances, notion of distance between our data and our model. And if we have such a distance, there's sort of three things we generally sort of look at, which is we can given a model, we can try to sample for it by finding points that minimize the distance between this set of points and our model. We can do model checking, where we take a data set and hope that it aligns with our model, and that means, in a sense, that our discrepancy is close to zero. And finally, this is what I'll be talking about here, which is model learning. So you're given a data set and you want to find a model which models this data set as well as we can with respect to this discrepancy. And just to so discrepancies don't necessarily commute, and the triangle inequality may not hold. So which is why we I think of it as sort of the squared distance, which is maybe a bit vague notion. So as Thomas and Christian have talked about in the last two seminars, like our interest in my PhD is in protein. In protein folding and sort of 3D structure. However, in modern applied machine learning, we have sort of two core challenges, which is we work with fairly complex data. Now, the complexity comes from these, like in particular, from having components of our data points which are highly, which can have correlation structures, which is also what we're exploiting in our model. But we also have the problem of when we want to compute. So, for example, computational finance, the computation time of your model will directly impact the potential earnings of that type of model. And finally, we have the issue of like tall data. So the sizes of data sets, and this is particularly common sort of in language models. We're working with terabytes, and so the algorithmic approaches we take to this need to handle these complex data, but to be able to sort of learn models, we also we want to be able to postulate rich enough models to capture the data we're working with. And so like deep learning has been a major component of this, which hugely over parameterizes the problem, and then we're able to distill out sort of a winning ticket. But complexities, there's of course complexities in other types of models which directly impact the type of the way we're doing our learning, from classical machine learning like k-nearest neighbors or sort of LVA to these Bayesian methods like the work by Thomas, Bayesian neural networks for protein structure prediction, and what Thuesen was talking about, Christian Thuesen was talking about last time. Okay, so just to make it more concrete, the learning problem that we're gonna or the way we're gonna formalize our learning problem is as inferring an unnormalized distribution. And the reason why we want it to be unnormalized is that this is just this p bar, this normalization term that is often interactable to compute for the type of models we're looking at, like Bayesian neural networks, for example. Whereas, so to make this problem, like these learning problems, computational, we'll be working with these unnormalized distributions. They're common in Bayesian inference, probabilistic graphic models, and energy-based models. Traditionally, in statistics, sort of Markov chain Monte Carlo have been the approach for working with these unnormalized distributions, whereas in machine learning, this is sort of strict dichotomy, stricter than this. It might be more fuzzy in reality, but the variational inference, where you're trying to approximate, like you're coming up with some variational distribution to approximate these unnormalized distributions, have been as they called. And then in machine learning community, sort of a late arrival on the stage is methods based on techniques based on Stein's method. And I'll talk about a particular instance of this, which is called Stein Variational Gradient Descent, and an extension which allows us to use sort of variational distributions within this framework called Stein mixtures. And then finally, our algorithm, ELBO-within-Stein, which is a method of inferring Stein mixtures. So just to remind ourselves, variational inference in a nutshell is we're given a data set. We have some hidden some probability model with a target distribution with which are hidden with some hidden latent variables, and then we take a computationally efficient class of distributions, like for example a parameterized exponential family. And we're trying to find a particular instance of this class of distributions that minimize the KL divergence, this notion of distance between the posterior of our variational distribution and the true posterior p theta. So so it's been known for a long time that we can sort of do this efficiently by maximizing this term we call the ELBO, and we'll do this you will use to do this with the natural gradient descent, which is just gradient descent that sort of adheres to a manifold. But Hoffman showed that actually if you choose Q to be an exponential family, we can do mini batch training. So that is, we can train on a subset of our data, of our total data, which means this now scales to a much larger data sets when we don't have to sort of do our evaluation of our likelihood on every single data point, which might be in the millions or trillions. For very large problems. So so just to give you an idea, so if we look at the initial data and true distribution, so the true distribution in red, and then I have a finite number of samples. Well, we can use SVI to find a parameterization of a normal distribution. So this is the mean location. There's a standard deviation, such that my variational distribution covers sort of the data and the true model. However, this is not necessarily a great model. In particular, if I have multimodality, which is not captured in my variational distribution. So one way to remedy this is the Stein Variational Gradient Descent, which is a particle method, and it's based on Stein's method. So I'm just gonna shortly introduce Stein's method and give some of the key terms, and then we'll talk about Stein Variational Gradient Descent. So the idea is to characterize our target distribution by some linear operator on a function space, such that when we take with respect to some other function, so think of this as sort of a variational distribution, such that for every function in our function space, which we call the Stein class, when the operator operates on this function, then the expectation under our variational distribution is equal to 0 for all functions. That's the same as saying that my variational distribution perfectly captures my target distribution. Now, we'll be interested in the space RD as our domain. Will be moving into real space, and if we introduce a further constraint that our score function, so the normal Euclidean normal score function, under expectation that this is finite, then we get this Langevin-Stein operator. This is work by Gorman and Macquarie from 2015 and 16. And this operator is given here. And so a natural thing just to check is sort of, okay, well, if P equals P, does this hold? And if P is not equal to Q, does sort of do what we expect it to do. Yeah. So let's make it simple. Have a one-dimensional problem and set P equals to P. So then our expectation becomes with respect to P, and we put in our Stein operator, expand it out, take the gradient, that cancels, and then if we do substitution by parts on this first term, then this will cancel, and we'll be left with evaluating f of x px at negative infinity. And if we sort of assume that they vanish, the probability vanish at the boundaries, well, then we have actually proven that that indeed if P equals itself, then we have that the Stein identity holds. Similarly, we can say, well, what if they're not the same? We need to be a little bit careful here. So we're gonna have so this is gonna be a transform, and where x is a distributor according to Q, and we now have this distribution when we transform to new x by this function here. And under this construct, Li and Wang, this is actually the Stein Variational Gradient Descent paper, they show that there's a relation between the gradient of the KL and the negative expectation, which we see in the Stein identity. And so because P is not equal to Q, we have that KL is greater than 0, which means just assuming that our Stein class is large enough, there's a function that decreases the KL. And so it's not equal to 0. So and this gives a notion of Stein discrepancy by choosing if you choose the supremum of this expectation, sort of where the distance is the largest, the difference is the largest, that's going to be our Stein discrepancy. So that sort of takes care of one part of it, which is our Stein operator. The other key aspect of this is the function space. And so we want it to be large enough to sort of capture interesting distances, but we also want it to be simple enough that we can efficiently compute it. And it turns out that if we choose a reproducing kernel Hilbert space for this, well, then we have these two properties, and further we actually get a closed form for sort of the optimal the supremum function, the supremum of the discrepancy. So and a reproducing kernel Hilbert space, just in short, is we have a Hilbert space where we have these kernels such that we can take any function here and we can write it as a closure of the linear span of these reproducing kernels. Okay, and if they're positive definite, so that is to say that these kernels greater than or equal to 0, or in particular strictly positive definite, which is a restriction on these two constants, this is only equal to 0 when all these CI constants are equal to 0. Then the reproducing kernel Hilbert space is dense in the space of continuous real functions. I should just note that 8,0 here, we're just going to choose our x to be R as well. So that means we can essentially arbitrarily closely approximate any continuous real function using functions in our reproducing kernel Hilbert space, which can be written as a linear span of kernels. Good. So so we're going to put a further restriction on this on our Stein class, and that is that we're only going to choose. We're going to construct this kernel Hilbert space by the product space of these. So because remember we want RD, and each of these gives us R. So we're going to do a product space on them. And then in this space, we're gonna only choose among the functions whose norm is less than or equal to 1. This is technicality, but it gives
Is it just me, or has Ola disappeared for everyone?
Yes, I thought that it was me, but I think Ola disappeared for everyone.
Yeah, okay, I had the same thought at first, but okay, he's gone for everyone.
For Jack as well. So maybe we should wait a while for Ola. Maybe he will.
Yeah.
Or if anyone has a more direct contact to Ola.
But Thomas likely.
Maybe.
Yeah, maybe. Yeah, I'll see if he's on the chat.
Huh?
Okay, something's happening. Ola,
yeah,
we have lost you. We have lost you for the last 1 minute or so. If you could repeat, you were completely off.
Is it better now?
Yes, I think you were talking about this product space and this unit val, and then afterwards we just lost you.
Okay, so let's go back to here. So we had this. So if we constrain ourselves to this product, to this unit ball of functions, then we can get a closed form for discrete measures. So that means the variational distribution will be a empirical distribution. So we take a set of points, we put a direct delta on each of the points, and we compute the average. So this is a restricted mixture. So yeah, and then we can find the supremum by this equation here. Okay, so this rushes us through to Stein Variational Gradient Descent. So what we're going to do is we're going to try to minimize the KL divergence between this set of points and our posterior of our target distribution. And in particular, we're gonna move these particles according to this update rule, where we take the current state of the particle and then we find this function which is in the direction that maximally minimizes the KL divergence between the transport measure of Q, so like moving the measure distribution of Z prime. And our target distribution. And remember, this is from earlier, this is directly related to the kernel Stein discrepancy through this relation. And because we've chosen our Stein class carefully, we can actually directly compute this optimal by the closed form here. And so just try to visualize it here, what's going on. So we have a finite set of particles. And so this function is going to give us, for every particle, it's going to move that particle according to some essentially a vector field.
Ola, because maybe I got distracted, and that's why I have not captured what is K here, the small K.
Oh, small K is a kernel. No, that's so I used to call it F. So these are these functions in the in the Stein class, but because we're using this special reproducing kernel Hilbert space, well, we can represent them, we can sort of express them as these kernel functions, and these kernel functions have some nice properties, such as they're positive definite.
Okay, got it. Yes.
All right, cool. So and yeah, the exact functional form, this kernels, there's actually quite a bit of work on this, but we'll get to it if we have time, a little bit at least. All right. I should also say, feel free to interrupt or ask questions or raise comments if you have any throughout. Okay, so just to write everything out, so we've chosen an empirical distribution of particles. We are moving them this update rule, which induces a transport. And so if we can think about, there's sort of a nice interpretation of this update rule. So this the first term here, so we call this a Stein force, because you can think of it as a force field. Just you can see every point has sort of gives you a direction of movement, and then you have a step size epsilon. And you can think of the first term here as moving us to, so this is the gradient on the score, so it's moving us towards the modes of our target distribution. Okay, and this is then scaled by the kernel. And you can think of the second term here as moving particles away from each other. So like as the 2 points get close to each other, the gradient becomes large, and then it will sort of make sure that we get a good spread in particles for that we get a spread so they don't all collapse to the mode, which would be happening if we just had the attractive force. So using the current example here, we can infer. So I've done this with our library. We can use Stein Variational Gradient Descent to sort of find a set of particles. So there's 100 particles here to approximate our data. And then the black line gives us the sort of a Gaussian kernel density estimate of these particles, and you can see it's certainly better than the normal distribution with the with the variational inference we had before. We can capture modality, for example, which is one of the really nice properties about with the particle-based methods is exactly that if you have multimodal distributions, you can have, or more in general, you can have very rich correlations between these particles. However, there's also a limitation, which is, so I needed 100 particles here to get a good estimate, and this grows exponentially as we go up in dimensionality of our target distribution. And so Nalsnik and Smith suggested to overcome this using variational distribution. So each of our particles now have a neighborhood defined by some variational distribution. Think of it as like a normal, for example. And so our update rule, here our score now, this is now a hierarchical model. So we'll have a variational likelihood, and then we have well, this is sort of a distribution over models. In Nalsnik and Smith's work, they sort of say this term is dominated by this term, and so they drop it. And then they can approximate this variational likelihood using importance-weighted Monte Carlo gradients. So that is to say, they're able to compute an approximation of this through a scheme. And what you've gained now is that you have you can use much fewer particles to represent represent your target distribution, because you have this notion of a neighborhood for each of the particles. there's some limitations to this. For example, because we're using an empirical distribution, we can't actually represent weighting between if we have a sort of a mixture model, so they will all be uniformly weighted. And you can get around this by having more particles, of course, but it is usually quite tricky to sort of match this well. I tried this with 3 at a point, and I could get it to become better, but as I said, it took a while. Okay, but the key thing here is what we've gained now is we've reduced the number of particles we need to represent our target distribution, and we've done so in a sort of a we've done so given an approximation of this variational likelihood. So instead of doing this approximation, which I'm not going to go into more detail about, you can use the Jensen's inequality on the variational likelihood to recover the evidence lower bound. All right, which is what is also what you were seeing from variational inference in the beginning. And so ELBO-within-Stein is taking this score function that we were using for Stein Variational Gradient Descent and replacing this by an ELBO. And that is the core, and then we get our update rule from Stein Variational Gradient Descent. So this is now a hierarchical model, but it's like in terms of it, this gives us an exact construction. The Smith and Nalsnik's method, we can actually also, we believe, recover an exact construction using Vineyard divergences, but I'll not talk about that here. Cool. So what I'd like to do now, let me just check the time, is I've coded up. So Christian Tugesen at the last talk, restarted. He was talking about Bifrost, which was a deep Markov model. And so, yeah, all right, this might take a little bit longer than intended because it restarted my, so okay. Anyway, he was talking about this deep Markov model. Now I'd like to show you, just do Bifrost for you here live, but I'm still missing some visualizations. So instead we'll use a similar type of type of model to produce music. In particular, we'll be producing some Johannes Sebastian Bach. And we'll be doing it with a probabilistic programming language called NumPyro, which I work on, and which so this ELBO-within-Stein inference algorithm is also implemented into the main distribution. Good. So we just need some imports. Oh, maybe let me just check here. It actually has. So one of the, I remember if we think back, then we were one of the key aspects here is that in terms of complex data is that we needed to work with to scale to tall data. That is, we need to also be able to use our hardware well. So Colab and Google have these TPUs available to us, which allows us to do acceleration of linear algebra operations if we use a library built for this. So and NumPyro builds on top of JAX, and JAX allows us to use both GPUs, and multi-core CPUs to do a computation. So we get sort of distributed computation, essentially working with a modern hardware. Yeah, we want to do a visualization. We have. So in NumPyro, you're able to define our variational distribution and our target distribution as a Python method or Python function, and then we have sort of special operations which are handling the stochasticity that's available in the model. Now, in the interest of time, I'm just gonna skip over this part of the model and the guide. If you're interested, we can talk about it either during questions or offline at some point, and just show you the data set. So what we're working with is we have these quarrels, which are piano rolls. So we have 88 keys, and whichever one is pressed down on a chord is given at that position, we put in a 1. So this is what our data look like, and we can visualize this. So we have our time dimension, so as we play, and then the chords here on our y-axis. This is dynamic in length, just like you would have with proteins. You would have the length of like until you do a multi-sequence alignment, at least you would have dynamic lengths, which is also why our data consists of our the sequences. So this is our tunes, and each tune's particular length, which we need to correct for when we're computing likelihood, so we don't compute longer than this particular music pieces. But because we're working with tensors and we want to be able to do efficient computation, we need to sort of make them all the same length. So we make them all the maximum length, and then just mask out according to each data set. In JAX, we're explicit about the state of the random number generation. This might be unfamiliar if you come from something like Pyro or Stan or other PPLs, where this is handled in the background, but in JAX we have to explicitly say what the state of the random number generation is. So with a model defined and a guide defined, what we can do is we can instantiate our variational inference here. So this is going to be Stein's. So this is ELBO-within-Stein. Just to compare, this would be stochastic variational inference. So the first I showed you, and we're using the trace ELBO. We could also use the Renya ELBO to recover Nelsnick's and Smith's method. And then the two new concepts, right, is the choice of kernel. So we're going to use a radial basis function kernel. And then we need to specify how many particles we're using. Yeah, we can run inference on this. We give it the data, we give some hyperparameters. In particular, we're working on a subsample of the data. So we only use 50 data points at the same time. Now there's operators which sort of handle this for us within the model and choose random data points. If that choose random data points, assuming that our subsample size is smaller than the number of data points I have in my data set. Inference takes about 2 minutes. I've already run it earlier in the interest of time. Sorry. And then we get this results object back, and what that contains is our sort of the Stein force computation at each of our time steps. Let me just make this slightly smaller. Can you? I hope this is still visible. So we have a step here and our Stein force or our loss here. This little bit of uncertainty is because variance is because we're computing on a different subsample at each time step. But and like the key, like we usually use this as a diagnostic, and the key thing to look for is it's decreasing and this variance does not increase as we go over time. Cool. So once we have our trained model, we can grab the parameters and we can do a prediction. So I'm just going to load up the validation set, and then we can. Oh, this doesn't actually take that long. We can sample. So what we're doing here is we're sampling. So what it's actually using here, because we have predictive true, is we're only using the length, so we're just sampling a length number of data points from our predictive posterior, and we end up with sort of a generated GOR like this. And if we compare that to our validation data set, I mean, I haven't tried to play it yet, and I'm not gonna. I was gonna try to play it here, but getting the audio to work is sometimes quite tricky when you're in a conference call. But we see some structure here, like we have these sequences or nodes that are held for long times, and and actually, if we compute, so standard measure, this is negative log likelihood. If we compute the negative log likelihood of the generated sequences, it's also low, and it's in particular lower than you would get with SVI. So we also have some performance indicators that tell us that this is actually doing pretty well. That was that was just to rush through through this through this particular example. So let me just finish up here. So there's a lot we haven't covered. We haven't covered kernels. You saw one kernel. There's 6 kernels at the moment in our EinStein library, which is what we were using to do the inference. In particular, so there's matrix kernels, which allows us to do for example, precondition with the Fisher information. One thing that we don't have available is probability product kernels. So once you have a variational distribution, you don't want to treat the mean and the variance if your variational distribution has those two in the same way. And so there's a class of kernels which will sort of take the information geometry into consideration. Another interesting approach based on kernel Stein discrepancy, these Stein points, which started out being sort of a global optimization where you set a grid of points and then you globally optimize them to fit your target to cover your target distribution. These have and was then extended with Stein point MCMC, which makes it more efficient to compute. These are some very nice properties like quasi-random numbers where you get space covering samples. This is in our EinStein module, where we expect probably to have a publication on it later this year. However, it's not in the main NumPyro distribution. Kong-Lee gave a connection between Stein Variational Gradient Descent and gradient flows. I have not explored this myself, but it's interesting work and something I have on my own to-do list. Max Welling's group came out with equivariant version of Stein Variational Gradient Descent, this NeurIPS. So that's also an interesting direction to take this in particular for protein folding, where you have so equivariance allows us to sort of handle symmetry groups such as rotations. And finally, like this gradient flow work has led into some mechanics for choosing the bandwidth of the real basis kernel, which turns out can be quite important for getting good representations of our target distribution with these kernel-based methods. Yeah, so this is joint work with Thomas Hamelryck, my supervisor, and Christoph Lai, my co-supervisor, and finally Ahmed, who's our assistant professor in Thomas's group. Ahmed built the first version of EinStein, and we still just work together to get it to the state where it's published in a framework. This is work funded by the Free Research Foundation of Denmark, or Danmarks Frie Forskningsforbund. little bit of plugging. I'll visit Luxembourg from the 6th to the 17th of March. So if you found this interesting, or any of my, I sort of tried to put some of my other interests here, in particular, HMC for when you have many data points, protein folding dynamics, which is the topic of my thesis, more generally probabilistic programming languages, more general than necessarily particularly NumPyro, or directional statistics. Feel free to contact me, or Christoph or Thomas.
Okay, thank you, Ola, for your very nice presentation and the crash course to Stein Variational Inference method. Very, very nice, and I'm sure that Sorab and for sure I will be happy to talk to you once you will be in Luxembourg.
All right.
So I'm opening the question part, so everybody, anyone who wants to talk, can switch on your mic and maybe camera and talk and ask questions.
Hi, Ola. Thanks for the very interesting talk. I have a few questions. My first question is that what extra information do we get by using the Stein's variational inference compared to the classical variational bias? And, yeah.
Okay, so you're asking, so that's a good question. So the main thing you get is you are able to capture these sort of rich correlation structures much better. So when you're using variational inference, you have to pick, in the notion of having a variational distribution, you have to pick a variational distribution. And that the properties of that is going to also enforce the properties of the generative model you're able to learn. Particles are able to move relative to each other, and as you could see in with the Stein Variational Gradient Descent, like they interact, right? Like the kernel is a function of particle pairs. And so that's like that's the main gain. In concrete terms, this means something like capturing multimodality. You can do directly with these particle methods, whereas you have to either start using mixtures, which introduce if you you start working with hierarchical models. So mixtures, you have the problem that you can't actually compute their entropy directly, so you have to introduce an auxiliary distribution to make this actually tractable. So you end up with a much larger problem you're trying to tackle, or you start going into hierarchical models, which cost you extra gradient evaluations, as it turns out, when you're sort of writing out the inference. So it becomes longer it takes longer to run it effectively.
So this method is faster than the classical method?
That's a great question. It's certainly not faster than Stein or SVI with just a normal distribution. But actually you can if you choose one particle and you choose if you choose one particle and put a normal distribution on that particle, you recover SVI. But it's sort of from a computational view, it's sort of embedded into this Stein Variational Inference framework. So you end up doing some extra compute, but then the time becomes comparable. So for the example I was showing, you would probably be able to run this in a minute with SVI, and it took 1 minute and 30 seconds with Stein Variational Gradient Descent with 5 particles. Also, the computation time is a function of the number of particles. If you use 100 particles, it's going to take longer.
And why did you use 5 particles?
So that's a good question. So turns out there are results on the number of particles you need to cover things well. However, they are cumbersome to use. So usually this is a heuristic. My go-to, it's a hyperparameter. The best way to go about this, assuming you have the computational resources available, is just to do a grid search, like do 2, 5, 10, and 50.
Then my last question is that why do you use NumPyro? Because I see other frameworks are more popular, and I once tried it for HMC and NOTS. It was not that fast. So why do you use NumPyro? So
the reason we use NumPyro is actually because it's based on JAX. And what JAX can do is you have this XLA. It combines XLA and autograd. Right, so we want autograd because we're computing all these gradients. XLA at the moment is on most benchmarks, or not actually not most, all benchmarks I've seen, the fastest general purpose tensor library in Python. So that's why we're using JAX. They've come up with a special version of Hamiltonian Monte Carlo, which allows us to sort of cache our computation tree. So you can do Hamiltonian Monte Carlo with JAX acceleration. Now, with that said, it doesn't. If you're using multiple GPUs, for example, or if you're running this on CPU, you don't get a gain. Like this is really written for GPU acceleration or TPU acceleration. So if you compare to something like Stan on CPU, you would definitely see much better performance with Stan. However, you shouldn't be doing things in sort of. You should be using parallelism. All hardware is parallel.
Thank you very much. Thanks.
Hi, Ola.
Hello.
Thanks a lot for the nice presentation. I really loved the pace, and I had many questions, but you subsequently answered them during the presentation itself.
Oh, thank you.
And okay, but I would ask this, that as you said that, so you have the number of particle and even the choice of the kernel as the hyperparameter, and I suppose that it must be tricky to choose that, right? How do you?
So I showed the RBF kernel, which was the one that was originally suggested in the Stein Variational Gradient Descent. There's a subsequent paper that shows that if you're using, first thing I should say is the type of problem you're working with will sometimes enforce a kernel for you.
Okay.
So if you're working with graphical models, you'll use a graphical kernel. This is the thing that will be able to express the type of model you're working with. But if you're just working with sort of model on Rn, what's called a IMQ kernel is actually shown, proven to outperform RBF kernels on a quite large set of problems. These matrix kernels is really what you want to be using if you have the memory available for them. They're a little bit expensive, but they allow you to take. So it's like going from doing gradient descent to quasi-Newton, where you can sort of take the curvature into consideration, so you don't have to worry about your step size. But yeah, it's a hyperparameter. Sometimes you're lucky and your hands are forced, but it's RBF and IMQ, you would be the two common choices, and if you can, you'd use matrix kernels. That is a great question, and there's not a very good answer for you, Simon.
Because particularly when you have a higher dimensional problem, then it's even difficult to do this, let's say, trial and error procedure.
Ooh. Oh, absolutely. Like my counter to this is if you're using something like SVI, now you're just stuck with the choice of which variational distribution you're using. The neat thing is, so just like with SVI, you have these constructs which can automatically generate for you the variational distribution. So you just have to give it the model, and you can sort of. But if you're using a normal, it's not that hard to put the mean and automatically on every place you have a sample statement. And the same is true for these kernels. So you don't have to implement them in a per problem instance. We have them available. So you just like you'll do something like RBF kernel, and then you could do Q kernel. That's the one. So like some of the pain is taken away in that you don't have to code them yourself, unless you want something very specific and custom. But yeah, no, it's certainly a.
And another thing would be that I am particularly interested in, me and Jakub, we were working on using variational inference in context of neural networks, and you have millions of parameters. And then when I was thinking about this, it's still quite computationally costly. I mean, when you increase the number of particles, and it gets quite computationally costly. And do you know that have there been some efforts already started in using the Stein variational in constant context of the neural networks?
Oh yeah, so this is a deep Markov model. So there's a recurrent neural network in here, a GRU. There's we have a dense network here, and also in my model I have 2 neural networks. So like this is using amortization, and the net, like I think I have something like 200,000 parameters in the model.
Okay, thanks. And just one comment, I guess even TensorFlow probability now, it also, I guess, can work with JAX.
Yes, and TensorFlow probability I really like, in the sense because it allows you a lot of freedom in terms, or it's very expressive. Like what's advantage with something like NumPyro is it sort of comes with some batteries for you.
Okay. Thanks a lot.
No problem.
Ola, I have a question about the demonstration example that you showed.
Right.
Do you think we could somehow publish the link to this, or is it publicly available?
Yeah, so
play with this a bit.
That was my intent. I'll send it to you. I just need to. There's this thing. Like I have a couple of like I define my neural networks elsewhere, so you don't have to look at all of that. And that means I needed to connect to mine. I'm sure this is something I can solve. I just didn't have time to it. So once I've solved that, so that part is publicly available, then I can then I'll send you the link. Because it's a collab now, so it's like I can just share this with you. The problem is that, and you would be able to have the code, but you wouldn't be able to run it because you need access to my drive. But I'll fix that and I'll send it to you.
Okay, great. Thank you. Thank you. So, any more questions? Okay, if not, let me thank our speaker again. It was a really nice presentation and discussion, and I think feel invited to contact Ola either offline or whenever he will visit us in Luxembourg. So next week we'll have a machine learning seminar, exceptionally at 3 p.m. because we'll have a speaker from California, from Stanford, Professor Lester McKay. And so just stay tuned. I will send out the invitation, but bear in mind that it will be exceptionally at 3 p.m., not at 10 a.m., just because of the time difference. So thank you all for the nice discussion, for your attention, and the speaker again. And see you next week. Bye-bye.